Radiomics is a multidisciplinary science that aims to quantitatively analyze diagnostic images to provide information on the tumor pathophysiology, which cannot be qualitatively appreciated by the human eye. This is done through feature extraction. Radiomics features are mathematical descriptors calculated through a statistical analysis of the spatial distribution of voxels of different intensity within the image. The radiomics workflow includes the following steps. The first is the image acquisition. The second is the segmentation of the volume of interest. The third is the feature extraction. The fourth is the selection of the relevant features. And the last one is the setting of a predictive model to classify new inputs. The features can be divided into various categories. The main ones are the morphological features that describe the geometry of the volume of interest, such as area and volume. The first-order statistical features, calculated starting from the image histogram. The higher-order statistical features, calculated starting from matrices, which preserve the spatial relationship between the neighboring voxels and provide information on the texture of the region of interest. The aim is to identify a radiomics workflow that can provide a relevant prognostic model based on a real clinical problem of a dataset of 56 patients with brain tumors undergoing MedPET examinations to distinguish low and high-grade tumors. Since there is an high uptake of FDG in the cerebral cortex, the identification of low-grade tumors is difficult. For this reason, we investigate the diagnostic power of methionine, which is an amino acid involved in protein synthesis and is modified in tumor cells. It's selectively captured in the tumor region, making easier tumor identification. The histological information is useful from a clinical point of view because it influences the patient management and the prediction of the biological behavior of a tumor. Being a retrospective study, the first part of the study was the collection of the images of patients with known histopathological results, using two sets of images acquired with different scanners to increase the statistics. The collection provided 56 MedPET studies. After collecting the images, the next step was to identify the volume of interest to extract the radiomics features. We used LifeX tool. It provides a graphical interface for the visualization of coronal, sagittal and axial sections and includes tools for creating and editing the volume of interest. First, a pre-processing of the image is necessary to homogenize the sample. A resampling was carried out with 64 discrete values between 0 and 20 SUV units. The voxel sizes instead remain the native ones. Although manual delineation seems the most intuitive, it's subject to variability among observers and provides irreproducible results. An operator-independent segmentation method is required. In our study, a threshold method was applied. The user must identify the area containing the target to avoid false positives. Subsequently, the algorithm carries out the steps automatically. An intensity threshold T is set. Each voxels with an intensity greater than the threshold will be labeled as a tumor. Voxels with lower intensity will remain outside the segmentation. Starting from the identified volume of interest, 44 features are calculated. For each patient, two different segmentations were obtained. One relating to the volume of interest of the whole segmented volume, and one relating to a fixed region of interest of 81 voxels centered on the SUV max, to eliminate the dependence on the volume. The extracted data were inserted into a matrix composed of n rows indicating n patients and m columns indicating m features. Each row is associated with the relative gold standard 0 and 1. However, not all features provide important information. For example, some of them may be redundant. so a feature selection and reduction method must be applied. This method is based on the hypothesis that a combination of several features can provide better results than a single one. However, the identification of a combination of features among such a large number can be expensive in terms of time and memory, so a new strategy is implemented using the point biserial correlation, which calculates the correlation between the single feature and the dichotomous gold standard, in example 0 and 1. Based on this value, the features are sorted from the highest to the lowest point biserial correlation. Successively, we implement a while loop, in which a logistic regression is performed for each column. One output of the logistic regression is the p-value. The logistic regression model that interprets the variable y is better as the p-value decreases. The cycle then ends when the p-value does not decrease. Applying this method, the following features have been selected. The last step represents the goal of radiomics and consists in the development of a machine learning model with the aim of classifying a new case starting from selected known data. In this study, a method based on the discriminant analysis was used. This is a supervised classification algorithm that is a process of predicting a qualitative response while starting from a set of predictors X. This task is equivalent to build a classifier, that is an algorithm that analyzes the training data and deduces an hypothesis to predict the patient outcome. In supervised classifiers, the training data consists of a series of examples, each of which represent a pair consisting of radiomics features of a patient with known outcome and the number describing his outcome. The classifier analyzes training data and provides an hypothesis, a function, which can be used to predict new outputs. At this point, the k-fold cross-validation has been integrated. The dataset is divided into k equal subsets, with k equal 5, and the holdout method is repeated k times. Each time one of the k subsets is used as a validation set, and the other k-1 subsets are put together to form the training set. When the training step is completed, the validation step is started to verify the performance in classifying new scenarios. Having predicted value and observed value, it's possible to identify true positives, true negatives, false positives, and false negatives. Starting from these values, the specificity is calculated. It indicates the ability to correctly identify subjects with high grade. The sensitivity indicates the ability to correctly identify subjects with low grade and accuracy. It's the most important parameter because it provides the percentage of elements successfully classified. A graph showing the sensitivity and specificity values simultaneously is the ROC curve. The surface area enclosed between the ROC curve and the bisector of the first quadrant provides an important value called the AUC, the value of the area under the curve. The ideal ROC curve should draw an upper left corner. Consequently, the higher the AUC, the better the classifier. The highest possible value for AUC is 1. The bisector indicates a random classifier. Results show that our workflow achieves good performance in terms of accuracy, which is greater than 70.31%, and specificity, which is greater than 71.81%, in all cases except when we consider both scanners that use fixed region of interest. Another result is related to the study on the difference between fixed and threshold region of interest, because if the threshold region of interest is considered, higher performance values are found. For this reason, we can conclude that there are no particular advantages in using an homogeneous region of interest, example fixed region of interest, rather than a segmentation algorithm that achieves a variable region of interest among patients, example threshold method. We report the ROC curve with the relative AUC values for each dataset, for the fixed region of interest, and for the threshold region of interest. Low performance values were found for AUC, in example less than 78.91%. The main cause is the low number of patients. Also, the patient dataset is out of balance. As can be seen in the table, for better performance, a machine learning algorithm should work with the same number of objects for both classes, low-grade and high-grade cancers, and thus be balanced. In our work, the group that shows the greatest symmetry is the one related to Siemens. In fact, in all the results we notice higher values. The last but most important result is that in all cases lower values are seen when the scanners are merged into the same all group. This is a particular limitation of radiomics. In fact, the features are influenced by acquisition parameters, reconstruction algorithm, slice thickness, voxel size, thus hindering multicenter studies. Radiomics is a new discipline, and for this reason it requires a standardization that involves the implementation of a defined procedure, including a post-extraction correction, which is applied directly to the extracted features. This could allow for easier comparison of features from retrospective or multi-center data across different scanners. To conclude, we note that the power of a machine learning algorithm lies in the quality of the data, where a greater number of features implies a greater number of samples. One of the main limitations of the proposed study is the relatively small dataset used for the training and validation phase. Hence, a future study with more data should yield even better results in improving the predictive model. Thank you for your attention.